you need a lot of mass in this region. So we've calculated you need between 1 to 10 Earth masses of minor planets in this region that need to be detected, just like Planet 9, or else this is a lovely theory, but it's not happening in the outer solar system. And Kuiper Belt is a terrible name, because as you saw, it was kind of like a cone structure, or if it is collapsing in physical space, it would be kind of a disk to one side. But it's exciting because people are looking for Planet 9, so they keep finding more and more small mass bodies. And they're very difficult to detect because they never come close to the inner solar system, they're detached. So if you detect one, and you know your statistics, your observational statistics, you can infer that you've got a huge population of bodies that are at aphelion that you're not able to actually see. Yeah?
So I assume that you're studying this because you need self-gravity in some sort of ratio like 10 to the minus 5 compared to the central gravitating body. Is that right?
Yeah, so it started off as a timescale argument for this to actually occur within the age of the solar system. But it is also to withstand the forces from the giant planets and get this important at like 100 AU.
Because I was going to ask then, like, is it robust against Jupiter?
Yeah. So once you get too close to Neptune in particular, your precession becomes too important. So those orbit average torques wash out. So it will really depend on the mass in the disk. Like, where should you start seeing self-gravity become important? The observations say somewhere around 200 AU right now. So this is something I'm working on with a grad student. Like, what does that say about the mass? Irrespective of the time scale, what is that telling you about how much mass needs to be involved?
So,
yeah.
So if I understand correctly, what you're saying is that your prediction is that there's a substantially more amount of mass in the Kuiper Belt than is currently thought. And
outside the Kuiper Belt, yes. No, outside the Kuiper Belt. So,
outside, okay.
So like hundreds to 1,000 of AU.
So are you going to also, does this lead into the Oort cloud, or are you going to talk about that as well? Or?
Probably not. I need to switch to galactic nuclei. The reason I don't think this is important going beyond 1,000 AU is that your orbital periods become really long.
1,000 AU is basically the start of the Oort cloud, according to some people, so I don't know.
Yeah, the way I think about it is, like, we can explain the scatter disk, and then it's kind of, we didn't see anything for a long time beyond like 100 AU, so it was like, it's probably empty. And that's what simulation showed until you get to the Oort cloud. But those simulations with massless test particles. So you scatter things out there, and all they do throughout their entire lifetime is then get rescattered by a giant planet. Once you include masses and let them gravitationally interact with each other, they want to detach. And they want to take each other away from the influence of the giant planets so they can sit out there. So all the massless test particle simulations today that show this region empty, they wouldn't have been able to get a huge amount of mass in this region. Once you get beyond 1,000 AU, your timescales increase. So I think that the classic Oort cloud should not be interested in self-gravity. In this way, the orbit average torques will just take way too long to actually become important. Passing stars and things like that take over. Okay. Any other questions, or we're happy to leave? Yes.
So you talked about the trend and the inclination, but what about the distance and perihelion? Do they become more circular, or so they wouldn't show up like one of them wouldn't become closer and show up like Avi's spaceship or something?
No, they all become more circular. Just as you incline, just conserve angular momentum, absolutely all of them drop in their eccentricity. So there is some scatter, and after this instability saturates and there's more of a cone distribution and they're not on the disk, they can still torque each other. So some might go to eccentric orbits, but there's not like a net flow back to low perihelia orbits. Most of them stick more circular orbits, making them really hard to find. Yep.
So what would Mike Brown and constantly what they can say about this?
They've been really good. To my face, they've been really good. They've been really nice. They've been wonderful. So I had this paper out with Mike McCourt before the Planet 9 paper came out. And so they mentioned our work, and they just said, like, this is really interesting. Unfortunately, there's no evidence for 10 Earth masses of material out there. To which I would like to respond, there's no evidence for a 10 Earth mass planet.
So you're both wrong.
So we're both demanding the outer solar system have a lot of mass. Planet 9's easier to detect, and it's got more resources, I think. But this needs nothing new, so I've got a little bit of an advantage that I can be like, small things exist. They've existed for the age of the solar system. They all got scattered. Everybody's very happy with like, they all got scattered. This is how we create the Oort cloud. If you include masses, they all want to detach and they can stick out there. So nothing new, it's just gravity. Doesn't mean I'm right, but I'm right. That's what I feel. Oh, okay, so before I move on, I just want to point out this is the work that my grad student Alex has done in Boulder. And one thing that's been really interesting that jumped out of this, we want to look at the time scales, we want to look at how much mass needs to be in this structure, but we cannot simulate the real solar system. So Alex systematically, painstakingly ran simulations with increasing number of particles, but with the same amount of total mass in the system. And what he found was really surprising, and we can only really just put it up in one line. If you don't have enough particles in your simulation, two-body relaxation, that scattering process, keeps kicking your particles off the orbits they would otherwise be on. And so you dramatically suppress these kind of orbit average dynamics. And it's not real, it's artificial because you're not simulating with enough particles. And so there was another paper by Konstantin Madigan and one of his students saying in a real solar system, this instability doesn't really work and it's due to maybe influence of Jupiter or something like that. And we could really easily tell, it's like, no, you've got too few particles in your simulation. So you can't actually reproduce this. Anyway, okay. I want to move on. I don't have time. Could somebody tell me the time? Oh God. Okay. So the second half of the talk, really quickly, I'm looking at the opposite case. When you start off with something circular, coplanar, you make things eccentric, but you pile all the orbits onto one side. And so I'll be talking about this in the context of galactic nuclei. And this isn't actually going to take up half an hour. This is a shorter part. So I like to tell the story using the Andromeda Nucleus. So this is an image from the Hubble Space Telescope. For a long time before we had Hubble, all we could see was some kind of asymmetric structure. We weren't able to resolve the nucleus of Andromeda. This is within the radius of influence of the black hole that's located here, roughly. So we can see two bright peaks in starlight, and the most obvious solution to what are we looking at is that there's two star clusters in the center of the Andromeda galaxy, which is exciting because they're going to merge into dynamical friction. But if you calculate the time scale for calculating how many stars are here, how many stars are here, it's really short on the scale of millions of years. So it kind of tells us something odd is going on. Why would we just get lucky to suddenly see a merger of two star clusters in the center of our nearest galactic neighbor?
It's two black holes, actually.
Yeah, well that could help, right? Two black holes in the center would be faster. The other problem with this idea of like, we're looking at the nucleus and maybe there's two star clusters, is that you take spectra, they're identical. So that's awkward. And they're very old, it's K-type population, so gigayears old. So Scott Tremaine solved the problem. He was looking at rings around Uranus, I believe, that had some coherent eccentricity to them. So these rings were not circular, they were eccentric, but also the eccentricities were kind of aligned with each other. So he noticed that this could actually explain why you get two brightness peaks around the black hole. If this is a ring of stars, an eccentric ring of stars, you get one furthest away from the black hole at apocenter, because stars slow down. That makes sense, so you get an enhancement of density there. The other, you get near pericenter if we're looking at the disk in a particular configuration, because the phase space the stars have to pass through along your line of sight gets squished. And so you get another overdensity in the starlight there. Okay, so this model has worked really well. He actually did it with only 3 rings to try and match with the observations. Now we can do it with lots more and look at the velocity moments and everything like this. And the model works beautifully. So we have this eccentric disk of stars around the black hole in Andromeda. Extremely massive. It's like 10 to the 7 solar masses. The mass of the black hole is something around 10 to the 8 solar masses. But it's not alone. So this is some kind of not controversial work, but I think not well-known work by Lara et al. In 2005, looking at the nuclei of early type galaxies and non-dust obscured nuclei of early type galaxies. And the statistics he drew out from this were that about 20% of these nuclei were consistent with having eccentric nuclear disks, but being looked at from different angles. So you don't always get a double nucleus. You often get just an asymmetric structure or a nucleus with a strange kind of dip in density profile in the center. These are just some examples from different papers.
How about Sagittarius A star?
No,
Nothing.
our own galaxy is really boring. It's a nuclear star cluster, so it's rather symmetric, but it is weirdly flattened, more flattened than we would expect from its rotation. But it's nothing as interesting as this. So I just want to point out, so Andromeda has this unusual structure, but it's not alone. It's just really hard to resolve the centers of other galaxies. And Andromeda obviously is extremely close to us. If we put Andromeda back by to 5 megaparsec, we wouldn't be able to resolve the double nucleus. It would go back to just being kind of an elliptical nucleus in the center. Okay. So why are these stable? So the disk in Andromeda is billions of years old, the stars that make up the disk. So unless it's a transient structure, we need to understand how does it maintain the structure itself. So there